Welcome dear viewers. In this module, we are continuing the characterization of nanomaterials. Today's focus is on 4 important characterization methods which are highly useful for the characterization of nanomaterials. The methods include transmission electron microscopy TEM, scanning tunneling microscopy STM, atomic force microscopy AFM and Auger electron spectroscopy AES. First of all, let us enter into the description of transmission electron microscopy. TEM is a very powerful tool for nanomaterial characterization. The principle of TEM is similar to that of optical microscopy. That means the basic principle behind transmission electron microscopy and our common optical microscopy are more or less the same. A primary electron beam of high energy and high intensity passes through a condenser lens to produce parallel rays of electron. The electron beam transmitted through the ultra thin sample film. The transmitted electrons again pass through a series of lenses and finally fall on the fluorescent screen. That is, in the transmission electron microscopy, we are probing the transmitted electrons, not the scattered or backscattered electrons. It should be noted that the image developed in transmission electron microscopy is a 2D projection, two-dimensional projection of the actual sample. Regarding the interaction of electron beam with a sample, several things may occur. This we already learned. For the sake of convenience, let us go through the interaction of electron beam with the sample. The incident beam of high energy electron, when interact with the sample, some secondary electrons SC are produced, characteristic X-rays may be produced, backscattered electrons can be produced, Auger electrons, then some electrons may be transmitted through the sample. The transmitted electrons are probed by the transmission electron microscopy. Regarding the instrumentation of transmission electron microscope, TEM has several important parts. The parts are a vacuum system in which the electrons are traveling through, an electron emission source simply known as the electron gun, a series of electromagnetic lenses called electron lenses, electrostatic plates known as apertures, a phosphor screen, a CCD camera, that is charge coupled device camera. These are the important components of a transmission electron microscope. Regarding the schematic representation, the picture shows a systematic way of arranging various parts in a transmission electron microscope. A high voltage developer and electron gun is at the topmost portion of the instrument. There is first condenser lens, second condenser lens. In between this condenser apertures are present. Specimen holder and airlock device is also associated. Objective lens and again one more aperture is there. The electron beam transmitted from the sample is detected by a fluorescent screen and camera which is placed beneath the sample. Now, it should be noted that the sample preparation in transmission electron microscopy is a risky job, is a difficult task. The most important, the prime concern is that the specimen should be of less than 100 nanometers thickness for a conventional transmission electron microscope. The sample preparation, of course, a complex procedure. The sample is prepared by using a copper grid. It should be noted that the specimen is placed in a copper grid that is less than 100 micrometer thickness and 3 millimeter diameter. The picture represents the copper grid used for the transmission electron microscopy sample preparation. The sample can be made thin by different mechanical, physical or chemical method. It should be noted that the sample must be as thin as possible. At least it must be with the thickness range of 100 nanometer. Now, high resolution transmission electron microscopy, notated as HRTEM. This is a recent development in transmission electron microscopic procedure to improve its performance and analytical value. HRTEM allows the imaging at the atomic scale. It is a phase contrast image and can be as small as the unit cell of a crystal. All electrons emerging from the specimen are combined at a point to image a particular plane. HRTEM has been extensively and successfully used for analyzing crystal structures, lattice imperfections such as defects, and for advanced material characterization. Selected area electron diffraction, SAED or SAED pattern, is another application of transmission electron microscopy. SAED is a crystallographic experimental technique that can be performed in the very same transmission electron microscope. Since the wavelength of the high energy electrons transmitted is few thousands of a nanometer and the spacing between atoms in a solid is about 100 times larger, the electrons can be diffracted. That is, electrons can undergo diffraction during the experimentation in transmission electron microscopy. SAED pattern will be a series of spots. Each spot corresponds to a satisfied diffraction condition of the sample's crystal structure. That is, from the SAED pattern, we will get a clear idea about the crystal structure of the sample under our consideration. This is a very important advantage of transmission electron microscopy. Now we can have a comparison between three important characterization methods, namely optical microscopy, transmission electron microscopy, and scanning electron microscopy. The picture represents a comparison of experimental setup for these three techniques. Left hand side represents optical microscopy experimental setup. Middle one represents transmission electron microscopy instrumentation, and instrumentation on right hand side represents that of SEM. From this picture, it is clear that the position of the sample as well as the position of the detector are different in three different cases. In the case of TEM, the position of the detector is beneath the sample since it deals with transmitted electrons. It is better to have a comparison between two prime characterization procedures, namely the transmission electron microscopy and scanning electron microscopy. In the case of transmission electron microscopy, electron beam passes through the thin sample, whereas in some electron beam scans over the surface of the sample, there is no transmission. In the case of TEM, specially prepared thin samples are required for the analysis. However, in the case of some, samples of any thickness can be used since we are focusing only surface in SEM. Specimen stage halfway down the column. However, in the case of some, specimen stage at the bottom of the column. Image shown on a fluorescent screen in TEM, whereas image shown on a TV screen in SEM. Image is two-dimensional projection of the sample in the case of transmission electron microscopy, whereas image is of the surface of the sample in the case of scanning electron microscopy. This about the comparison. Now, the advantages and disadvantages or drawbacks of transmission electron microscopy. The advantages include the fact that TEM offers very powerful magnification and resolution. It provides information on elemental and compound structure. Images are detailed and have high quality. The disadvantages are TEM is a very large and expensive method of analysis. Sample preparation is very difficult. Operation and analysis requires special training. Trained pupils are required for its performance. TEM is limited to electron transparent materials. Images are black and white. It is not possible to get a color image in TEM. Now, another important characterization procedure. This is scanning tunneling microscopy. Acronym is STM. Let us have the details on instrumentation and characteristic features of scanning tunneling microscopy. STM is a technique that uses tunneling electrons to produce three-dimensional real space images of the surface of materials. Tunneling is a phenomena. I think you all familiar with the phenomenon of quantum mechanical tunneling. Tunneling means entry into restricted area. Tunneling electrons means certain case, certain circumstance, electrons cross the barrier and enter into restricted area. That phenomenon is called tunneling, simply quantum mechanical tunneling. That tunneling is utilized in scanning tunneling microscopy. STM was the first technique used to study nanostructure morphology. It is established prior to TEM. The working principle is that I already mentioned, nothing but quantum tunneling. An image is formed due to variation in tunneling current. As the tip moves across the surface, this we will make clear in further coming slides. The picture represents a schematic view of scanning tunneling microscope. In this instrumentation, there is a tip. This tip will move in a systematic way through the surface of the sample. It generates a tunneling current. That tunneling current is detected, and based on that tunneling current, we will get image of the sample, real-time image of the sample. Regarding the instrumentation, the important components are scanning tip, a piezoelectric controlled height and XY scanner, coarse sample to tip control, vibration isolation system, and finally an output device which is nothing but a computer or such a display system. The tip is often made up of tungsten or platinum iridium, even though gold can also be used for the generation of the tip of STM. The working of STM is briefly illustrated here. A very sharp metallic needle is brought near the sample surface as close as few nanometers. That is, when the sample is placed in a sample holder and the tip, which is made up of platinum or iridium platinum alloy, that tip is placed in contact with the sample, but the gap between sample and the metal tip is in the range of few nanometers. That distance is very important. An electric field is applied between the gap of the tip and the sample. A tunneling current flows between the conductive tip and the sample. The tunneling probability exponentially depends on the distance from the probe to the surface, and it can be mapped. The mapping can be by keeping constant current or constant height. That is, in order to represent the output, we can make either one as constant, either the current or the height of the tip, since these two are the variables in TEM analysis. Constant height and constant current methods. Just now I informed that there are two procedures where we can fix either one of the variable. The two variables are the height of the tip and current. You can make either the current as constant by keeping height as a variable or vice versa. That lead to two recording possibilities. Constant height and constant current methods occurred from that. Now, the advantages and disadvantages of scanning tunneling microscopy. The important advantages include high resolution, examination of roughness, surface defects and size as well as confirmation of the system. STM gives a two-dimensional image of the sample. Regarding the disadvantages, STM can be difficult to use effectively. It is not a cost-effective method. STM require very stable and clean surface, since the presence of impurity definitely interfere with the analysis result. STM use highly specialized equipment that is fragile and expensive. The third characterization method that we discussed in this module is atomic force microscopy, acronym AFM. Why the name atomic force microscopy? The first term, atomic. AFM can achieve atomic level resolution by using sharp cantilever tip. Images obtained by AFM can distinguish two closely spaced atoms, hence the term atomic. Then force. The image is created in AFM technique by quantifying the force between the probe, that is the cantilever tip, and the sample surface. So, there occurred a force, hence the term force. Microscopy. AFM amplifies the images. The instrument which is used for amplification is microscope. Hence, the name, the term microscopy. The working principle of atomic force microscopy. AFM can provide extremely high resolution images by using an ultra small probe tip at the end of a cantilever. The probe tip is placed at the tip or end of the cantilever. Cantilever made from silicon or silicon nitride having very low spring constant, which is a physical parameter. At one end of the cantilever, the very sharp tip is fabricated. The cantilever scans above the surface of the sample under our consideration. The picture represents the working of AFM. Here you can see the AFM cantilever, a laser beam, a detector, simply known as 4-quadrant photo detector. Now we can enter into the working of AFM. A piezoelectric crystal rises or lowers the cantilever to maintain a constant bending of the cantilever. Force exerted on the tip varies with the difference in the surface height and thus leads it to bending of cantilever. It is clear that the surface of the sample is not at all smooth. There may be height and depressions on the surface. Based on that, up and downs on the surface of the sample, the force acting on the tip of the cantilever may vary. A laser beam gets constantly reflected from the top of the cantilever towards position sensitive photo detector. The laser beam detects the bend occurring in the cantilever and calculate the actual position. This picture more clearly illustrates the bending of the cantilever with respect to surface up and downs. That is, AFM records a three-dimensional image of the surface topography of the sample under a constant applied force, which provides maximum resolution. There are three important operating modes for atomic force microscopy. In each case, we will get different information about the sample. The three important operating modes are the contact mode, the tapping mode, and the non-contact mode. The image obtained during each mode of operation is different. More discussion on this aspect is far beyond the scope of this discussion. Now, the advantages and disadvantages of atomic force microscopy. The advantages are: AFM gives three-dimensional surface profile of the nano objects, easily image non-conducting objects, can provide higher or better resolution. Disadvantages are the very low scanning speed. AFM imaging often leads to a thermal drift in the image, that is, image may get blurred. Due to the nature of AFM probes, they cannot normally measure steep wells or heights. It is better to have a comparison between two important characterization techniques that we learned. They are STM and AFM. Regarding STM, it gives a 2D image, whereas in the case of AFM, we will get a 3D image of surface profile of nano objects. STM records the tunneling current, whereas AFM records a small force between tip and the surface of the sample under consideration. STM uses a sharpened conducting tip, that is a metallic tip. However, AFM uses a conductive AFM cantilever. STM can visualize and even manipulate atoms. However, AFM can easily image non-conducting objects. The exponential dependence of tunneling current is the distance between the probe and the surface. However, in the case of AFM, the force distance dependence in AFM is based on tip shape and the contact force. Finally, in this module, we are discussing one more instrumentation, one more characterization procedure, that is Auger electron spectroscopy, denoted as AES. Let us go through the principles of Auger electron spectroscopy. First of all, what are Auger electrons and what is Auger effect? We will consider it in detail. Auger electron spectroscopy is a surface specific analytical technique that uses high energy beam as an electron source. Auger electron spectroscopy is based on the so-called Auger effect. Auger electrons are emitted from a surface when it is bombarded by an incident high energy electron beam. AES measures the kinetic energies of the emitted electrons, emitted Auger electrons. Now, what is Auger effect? A fine focused electron beam bombards the sample and ejects an electron of the inner shell of the atom. This vacancy must be filled by an electron from high energy outer shell. When high energy electrons fills the hole created in the inner shell, some energy is liberated. That energy is transferred to an electron in the outer orbit. That electron has sufficient energy to overcome the binding energy, and the work function of the electron is overcome, and that electron is ejected. This secondary electron is called Auger electron, and this effect is denoted as the so-called Auger effect. Picture illustrate the Auger effect. A high-speed electron knocks out an inertial electron from an atom, leaving a vacancy. Then one electron from the outer shell fill the vacancy. As a result of this, some energy difference will be there. That energy will be transferred to a electron which is placed in the outer shell. By utilizing this energy, electrons will again liberated from the outer shell. This second electron is called Auger electron. This effect is the so-called Auger effect. Regarding the instrumentation of Auger electron spectroscopy, there is a target. Target is our sample. Electron gun. Electron gun provide high energy electron beam. Electron beam creates the generation of Auger electrons from the sample. That Auger electrons are detected by the electron detector. Electron detector leads it to data acquisition, and finally the output is occurred in the form of an image. The merits of Auger electron spectroscopy. It is a popular method for the determining of the composition of top few layers of a surface. That is, it is an exclusive method for the surface analysis. All elements except hydrogen and helium can be detected with a relatively rapid acquisition time. Acquisition time is a spectral parameter. Why it is not possible to detect hydrogen and helium? This is because these elements have no inner shell, only one shell. Hence, there is no possibility for the emission of the Auger electrons. The interpretation of data in AES is not difficult because of the uniqueness of the spectral features. One-dimensional, two-dimensional and three-dimensional depth analysis can be performed with Auger electron spectroscopy. Thus, in this module, we have discussed 4 important characterization methods, their advantages, disadvantages, along with the applications and instrumentation. That all about this module. Thank you.